We've got two old favourites of optics, of course, a bunch of lenses, and we've got another favourite optical instrument, the laser. But we're not making a telescope or a microscope or one of these standard optical things. What we're demonstrating here is something that's more familiar in another context called strong focusing. And if I can demonstrate this, basically this bunch of lenses here is going to keep the beam confined to their centres no matter what we do up to a certain point. You'll understand what I mean. If I move one of these lenses now, you'll see the beam wriggle from side to side, but you won't see it escape from the set of lenses. Secondly, it doesn't go increasingly further and further off axis. It goes further and further on axis, and it even wiggles to and fro down the lenses. What's going on is that the lenses are much stronger than they need to be. They're magnifying lenses, which means that they are deflecting the light very strongly when the light goes slightly off axis. And it's that effect, that over-focusing, that allows the beam to be concentrated down the middle. And we can do quite a lot to the beam, and we can still keep it going down the middle. And I don't know whether you can see this is happening. We're still going down all that line of lenses, despite the fact we've moved some of the lenses, and we can move them to and fro, and it still continues to go down the row of lenses. And that is the strong focusing effect. Now, in a particle accelerator, a very similar effect is used, except the strong lenses are not glass lenses like these. They're electromagnetic lenses, and the beam is not a laser beam like this one. It's an electron beam, a positron beam, a proton beam, and so on. And that's the effect used at our big particle accelerator centres like Deutsche Elektron Synchrotron, DAISY in Germany, and like CERN in Geneva. Absolutely not. These are cheap as chips. So this is a lens from the high street, 50p a pop, magnifying lens. And this laser came, believe it or not, for a store famous for providing things for £1. And so it cost £1. Okay, so this is something you might not imagine is very common, bending light beams. Well, you can bend light beams, of course, if you use some optics. Here once again, we're using these very cheap magnifying lenses. We've got our £1 laser here, and what we're doing is we're deflecting it round an arc by using the fact that the lenses not only provide strong focusing, but they can also provide some deflection. And because we're sending the light down the edge of each lens, that deflection builds up. And over a whole set of lenses like this, you can build up enough deflection to go around 90 degrees, or even more. They need to strong focus, but they also need to bend things around in a circle. They want to repetitively accelerate something in a circle, so they have to deflect. So they have, as well as these focusing lenses, which are magnets, of course, they use dipole magnets, which in optical equivalent would be a wedge. So they would have a wedge, and then a focus, wedge, focus, wedge, focus, and so on. And each wedge or dipole magnet deflects and does no focusing at all, but the strong focusing magnets ensure that the beam stays in the middle of the vacuum pipe and allows them to accelerate it round a complete circle. Yeah, I think so. I think they just love the idea that you can bend light round circles, that light doesn't go in straight lines. Because, of course, they've learnt that light goes in straight lines. And, of course, it does in a vacuum. But once you've got stuff in the way, like glass, it doesn't go in a straight line. It can wriggle around. And they really like that you can bend light in circles. Because, they like learning things and then learning the exceptions to the rule. And learning why their teacher might be slightly wrong.